Okay. So we were doing this linear independence, right? In linear independence. Let me choose my color. Okay, so let's recall what we were doing. So in the last week we were doing this span of vectors. Okay, so we have k vectors, and then we consider linear combination of these vectors. The linear combination is of these vectors is called the span of these vectors, all possible linear combinations. Okay, so what is a linear combination? So for that we have to go back. A linear combination of k vectors is so you multiply those vectors by numbers and add them. Okay, so this is what linear combination means. So we were doing this linear independence last time. So what is linear independence and linear dependence? So we have these k vectors, and we call them linearly dependent if we can find some scalars a1 to ak, which are not all zero. Okay, some of them should be non-zero, such that their linear combination gives the zero vector. Okay, there's a linear combination of those vectors, which is the zero vector. If that is the case, we call these k vectors as linearly dependent. Okay, so the intuitive idea was that if the vectors are linearly dependent, then some of those vectors are kind of redundant. Let me see. Yes, I'm recording. Okay, so which means that even if I remove some of those vectors, I will have the same span. Okay, so for example, if three vectors are linearly dependent, then if I throw one of them, I still get the same span. Okay, and linearly independent is so k vectors are either linearly dependent or linearly independent. Okay, there are only two cases. So we did some examples, so we will continue with our examples this week. And okay, so let me give one more example before moving this. Okay, so this example is maybe it looks like the example we did last time. Okay, instead of that, let's look at this one. So this is an easy question. So let's look at these three vectors. Okay, so v1, which is a row vector. Okay, so it's 1, 0, 0 vector. And then we have v2, 0, 1, 0 vector. And then we have v3, which is 0, 0, and 1 vector. Okay, the question is, are these vectors linearly dependent or independent? Linearly dependent or independent? What do you think? Okay, let's look at the solution. Okay, so we look at the this linear combination, right? A1 v1 plus a2 v2 plus a3 v3, and we equate this to zero vector. Okay, so these are vectors. Sometimes I forget to write this vector symbol, but it should be clear from the context. Okay, so let's make it equal to zero vector. Then what is this? So if I put so this is really a1 times 1, 0, 0, and A2 times 0, 1, 0 plus, I forgot A3 times 0, 0, 1, and this equals the 0 vector, which is 0, 0, 0. The 0 vector for this vector space is the row vector 0, 0, 0. Okay, so if I do this operation, what do I get? I get A1. The left-hand side becomes really A1, A2, A3, right? The first component is A1, the second component is A2, and the third component A3. So this equals 0, 0, 0. So what does this imply? This implies A1 should be 0, A2 should be 0, A3 should be 0. That's the only possible solution. So what do we call in this case? Independent. You're right, Fatih. They are independent. Because if the only solution is a trivial solution, right? This is the trivial solution, then these vectors are linearly independent. Right? It says here. So if the only solution is a trivial solution, then we call them as linearly dependent. Okay, so these three vectors are linearly independent, I'm sorry. Okay, so yeah, let's give an example from another vector space. Let me know if you have any questions. Okay, this time our vector space is what is it? It is P2. I hope you remember this vector space. It's the vector space of polynomials of degree less than or equal to 2. Okay, so in this case our vectors are really polynomials. Okay, t squared plus t plus 2, and then the second vector is 2t squared plus t, and the third one is 3t squared plus 2t plus 2. Okay, the question is the same. So question is linearly dependent or linearly independent. Okay, so let's see how we do this one. Again, we consider their linear combination like this. So I don't want to write in full detail. So let's just write it like this. So A1 times the first vector plus A2 times the second vector plus A3 times the third vector. And this equals the zero polynomial in P2. What is the zero polynomial in P2? I mean, what is the zero vector in P2? It's the zero polynomial, as I said. I gave the answer. So it's 0. Okay, so this is a polynomial equation. So it will be satisfied if the corresponding coefficients of the powers of t are equal. So in t squared parentheses, we have a1 plus a2 plus a3. Okay. In t parentheses, what do I have? I have a1 plus, oh, I forgot 2, right? I forgot 2 here. A1 plus a2 plus 2a3. And finally, let's look at the constant terms, 2a1 and 2a3. This equals 0. Okay, so when is this polynomial 0? This is 0 if all these terms are 0, right? This should be 0. And this should be 0. Bakayım bir saniye Barış. Nerede? T kare. O 3A3 doğru. Beni çok iyi kontrol edin arkadaşlar. 3A3. Okay, like this. Thank you, Tugay. Okay. This is right. Okay, so we have three equations, right? Now we have three equations. Let's write the equations. We can really write this in matrix form, right? So the first, let's okay, let's write all the details. A1 plus 2A2 plus 3A3 is 0. And then A1 plus A2 plus 2A3 is 0. And finally, 2A1 plus 2A3 is 0. We have these three equations, and we can write the matrix form of this. It's better to work with matrices. Oops. Okay, so this is 1, 2, 3, 1, 1, 2, 2, 0, 2. And here we have 0, 0, 0. Okay, guys, before that, let me ask you a question if you remember this. So this is a homogeneous system, okay? It has three equations and three unknowns. So can we determine whether this system has non-trivial solutions? How can we make sure that this system has only trivial solution or only like has some non-trivial solutions? Barış yaklaştın. Determinant sıfırsa non-trivial var mıydı? Vardı. Evet, yaklaştın değil, doğru söyledin. So let's just consider the matrix, okay? So remember, okay, let me recall here. Recall. If I have n by n matrix and I look at this equation, Ax equals 0 vector. So there are two cases. If determinant of A is 0, then we have non-trivial solutions. And if determinant is not zero, if determinant is non-zero, then the matrix has an inverse, and the only solution can be found by taking the product with the inverse matrix from both sides. In this case, we have only the trivial solution. Only the trivial solution. Okay, so there are two cases. So in this case, we can just look at the determinant of this matrix instead of doing stuff with row echelon form. We can just look at the determinant because this is a 3 by 3 system. Okay, so what is the determinant of this guy? So let's look at the determinant. So when I look at the determinant, I erase this. So this represents determinant. Okay, just look at the determinant. So we can expand in the third row. So how does the expansion in the third row work? So it becomes like this, minus 1 to the power 3 plus 1. I'm looking at this term, right? Times that entry 2 times, if I erase that row and column, I get 2, 3, 1, 2. And then I get a 0 in the second component, and then I have minus 1 to the power 3 plus 3. And then, oh no, I write 2 here. And then what do I do? 1, 2, 1, 1. Let's compute this number. This number is 2 times 4 minus 3 plus 2 times 1 minus 2. What is the answer? So this is 2 minus 2, right? Which is 0. Okay, since determinant is 0, then we have some non-trivial solutions. Non-trivial solutions. So if we have non-trivial solutions, then what do we say? Let's look at here. So if there are non-trivial solutions, then we have this. Oh, wait a minute. Okay, if we have non-trivial solutions, then we call these vectors linearly dependent, right? Yes, it is. Okay, so they are linear. So in this case, they are linearly dependent. Okay, the answer is linearly dependent. Okay, so this determinant method is really useful. For this specific problem, there was an easier way. There was an easier way of seeing that these vectors are linearly dependent. Let's call this first way, okay? So let's call this first method. And there was another method. And the other method is, second method is, works like this. Second method. Second method is just observation. So when we're asked something like this, we try to observe. So in this case, you see that the sum of V1 and V2 really gives V3, right? So V1 plus V2 is really V3. So what does this mean? V1 plus V2 equals V3. I can write this as V1 plus V2 minus V3 equals 0. Okay, so this means linearly dependent. Why? Because so I can choose these coefficients as, let me make this another color. So this coefficient A1 is 1, A2 is 1, and A3 is minus 1. So there's a non-trivial solution of A1 B1 plus A2 V2 plus A3 V3 equals 0. Okay, so this also tells us that these vectors are linearly dependent. In this case, V3 is a combination of V1 and V2. So even if we throw away V3, it gives us the same span, okay? And of course, V1 is also a linear combination of V2 and V3, so we can as well throw away V1 and we get still the same linear, like we get same span, okay? Okay. Any questions? So this first method really gives us like a theorem, okay? So if we're looking for, let's write this as a theorem. So if we have k vectors, let's say we have k vectors, let's say in Rn, okay, so no, Rk. So these vectors are linearly independent if and only if determinant of the matrix. So I write these vectors as columns here. If the determinant of this matrix is non-zero and they are linearly dependent if the determinant of these determinant of the matrix which has these vectors as columns or rows is 0. So there are really two cases. So this is only true for k vectors in Rk, okay? Or yeah. So let me give you another example. So suppose we have k, so this is an example from R3. So let's consider these vectors. What are the vectors? 1, 2, 3. And then I have 0, 1, 2. And then 3, 0, minus 1. Okay, so the question is whether these three vectors are linearly independent or dependent. Okay, so for this case, we can really look at the determinants, right? So we just write the matrix. So all we have to do is check the determinant of the matrix. 1, 2, 3, 0, 1, 2, 3, 0, minus 1. So look at the determinant. If it's 0, then they are linearly dependent. If it is not 0, then they are linearly independent. So for this case, I think the answer is, wait a minute, did I write them right? 3, 0, minus 1, 0, 1, 2. 3, 0, minus 1, 0, 1, 2. Yeah. So this determinant is really 2. Okay. Then what does this mean? This means these vectors are linearly independent. Okay. So this method works for like 3 vectors in R3 or 4 vectors in R4 or things like that. Okay. So if there were just 2 vectors here, for example, if we were just given these two vectors and we were asked if they are linearly dependent or independent, we cannot check the determinant, right? Because determinant, we can only take the determinant of n by n matrices. We cannot take the determinant of non-square matrices. Okay, so if this third vector was not given, then we cannot use this determinant method. Okay, so you should keep this in mind. Any questions? No. Okay, another theorem. Let's see what this theorem is saying. So suppose we have, so we are always working in vector space, okay? Let's call it V. Then we have two subsets of this vector space, S1 and S2. they are both subsets of this set V, okay? S1 is a subset of V, S2 is a subset of V, but S1 is also a subset of S2, okay? So the thing is this, if the smaller set, which is S1, is linearly dependent, then can we say something about S2? So suppose S1 is 3 vectors. S1 consists of 3 vectors, and those vectors are linearly dependent, and we add more vectors to it. Okay, so suppose S2 is those vectors plus other vectors. What can we say about S2? Yes, Parish, it will be still linearly dependent, right? So adding more vectors to a linearly dependent set gives still a linearly dependent, because some of the vectors in S1 is redundant. Okay, so if I add more vectors, they will be still redundant. Okay, so if smaller set is linearly dependent, then the larger set is linearly dependent. Okay, so can we say something about the converse? So for the converse, if the larger set contains no redundant vectors, then the smaller set cannot contain any redundant vectors, right? So if S2 is, the larger set is linearly independent, then the smaller set is also linearly independent. Okay, so I won't give a proof for this one. You should, if you go back to the definition, you should see this for yourself. Okay, so as an example, for example, let me just give a try to not actual example, but so suppose V1, the set V1, V2, V3 is, if these 3 vectors are linearly dependent, then if I add another set to this, another vector to this set, this will always be linearly independent. Okay, so if these 3 vectors are linearly dependent, if I add a 4th vector to that set will still be linearly dependent. Okay. Okay, so that's it. And finally, let's look at the geometric idea of this linear dependence and independence once again. Geometric idea. So geometric idea is this. So let me try to make this larger. Okay, so in two-dimensional space, when are 2 vectors linearly dependent and when are they linearly independent? So 2 vectors, if they lie on the same line, like this, or there should be the other, let's do it the other way. So one is like this, the other is like this. So the vectors are on the same line, okay? Then maybe I should draw it like this. So if they lie on the same line, then these 2 vectors are linearly dependent. Okay, so because one is a multiple of the other, okay? And so to be linearly dependent, the vector should lie on the same line, okay? And to be linearly independent, they should not lie on the same line. So if these vectors are like this, so these two vectors are linearly independent. This is for plane R2. So what about in R3? In R3, when do three vectors, when are three vectors linearly independent, and when are they linearly dependent? Okay, so in R3, three-dimensional space, three vectors are linearly dependent if they lie on the same plane. Okay, so for example, if we have this plane, and all three vectors are on this, then these vectors are linearly dependent. Okay, they are linearly dependent. They could also lie on the same line, but a line also lies on a plane. So if three vectors lie on the same plane in three-dimensional space, then those vectors are linearly dependent. And if they don't lie on the same plane, then they will be linearly independent. If they were like this, and the third one, let's call it like this. Okay, then let me use my black one. Okay, so I'm giving the illusion of three dimensions. Okay, so if they don't lie on a plane, then those vectors are linearly independent. Okay, so this also makes the connection to determinant, right? Because determinant, if you remember, what is determinant? What is the geometric meaning of determinant? So determinant of these three vectors is really the signed volume. Okay, so it's the volume of this with a sign, and that sign comes from the ordering of these vectors. Okay, they should satisfy some kind of right-hand rule. So if the determinant is non-zero, we said that they are linearly independent. So determinant non-zero means they do not lie on the same plane. And if we go, the determinant of these three vectors is zero because they don't form a volume. Okay, the volume is zero. This is some kind of geometric idea. Let me know if you have any questions here. Sorusu olan var mı arkadaşlar? Okay. No questions. Then we move on to the next section. Okay. So next section is 4.6, and it's about basis and dimension. Let me also put the date for today. Let me see, where did we start? We started here, right? So how should put it? Let's put a date here. Okay, so what is the date? It's 27. 27/04/2022. 2020. Okay, so basis and dimension. Okay, now we start with a definition. Definition. Suppose we again start in a vector space. Vector space. Okay, and we are given k vectors. And we say, we say that these k vectors forms a basis. Let me make this, okay, forms a basis. So let's, this is important term, okay, basis for V, for the vector space, if the following two conditions are satisfied. This is a definition, okay, not a theorem. This is a definition. The first one is the vectors are, the vectors should be linearly independent. This is the first part. And the second part is the vectors should span the vector space. So span of these vectors should be the vector space. If these two conditions are satisfied, then we call this set of vectors V1 to Vk a basis. Okay. Now, first remark is this. So the first remark is, if let's say this, if these k vectors, if k vectors form a basis, then they necessarily must be distinct. The vectors must be distinct. They shouldn't be identical vectors in this set. And none of them should be zero. Okay? Because if you put if you put the zero vector, if you put the zero vector in this set, then the resulting set is always linearly dependent. Okay, so if you include the zero vector in a set, then that set will always be linearly dependent, because you can multiply the zero vector by any number, okay, and it will give you a non-trivial solution. Okay, this was an important idea. Maybe I should write it as a theorem somewhere here. Okay, so the theorem, if at least one of the vectors, at least, whoops, if at least one of V1 to Vk is the zero vector, then V1 to Vk is surely linearly dependent. Okay, so let's zoom in here, so make that this stand out. Okay, so this is a theorem. So if at least one of the vectors is the zero vector, then that set must be linearly dependent. Why? Because if I consider a linear combination of these vectors, then I can multiply the zero vector by any non-zero number and it will still be a solution, right? If I multiply all the rest by zero and multiply the zero vector by a number, then the combination will give me the zero vector. Okay, so let's go back to our discussion. So for a basis vector, none of these vectors should be the zero vector, okay? All of them must be non-zero and they cannot be equal to each other, because if they are equal to each other, then they cannot be linearly independent, okay? So let's give some examples now of vectors, basis vectors, I'm sorry. So the standard basis vector for, let's say, R2. For R2, these two vectors form a basis, 1, 0, and 0, 1. Okay, sometimes we call them as I and J vectors in physics. Okay, so these vectors form a basis. You can see that they are linearly independent. Okay, and you can also see that you can get any vector in R2 by linear combinations of these two vectors. Okay, so let's look at it. So okay, they are linearly independent, right? So let's look at linear independence. So what does linear independence say? So I consider this plus A2 times 0, 1 equals the 0, 0. Then you see A1 should be 0 and A2 should be 0. There is no other solution. So we only have a trivial solution, which means linearly independent. And the second thing is these two vectors must span R2. So we should show span of these two vectors is R2. So what does this mean? This means there's a linear combination. So if I get any vector xy in R2, so any vector can be represented in R2 in this way, then I can take a linear combination of 1, 0 and 0, 1, which gives that vector. Okay, so I can write any vector in R2 by using 1, 0, by using the vector 1, 0 and 0, 1. Okay, x times 1, 0. If I go x units in the 1, 0 direction and then y units in the 0, 1 direction, I get the vector xy. So any vector in R2 can be represented as linear combination of 1, 0 and 0, 1. That shows that span of these two vectors is R2. And this basis has a special name. So this 1, 0, 0, 1 basis, it's called the standard basis, okay? So this is called the standard basis. Right, okay. So is it the only basis for our R2? No, it's not the only basis for R2. We can have other basis vectors, right? So let's give another basis vector for R2. I don't know, like 1, 0 and I don't know, 1, 1. Let's look at this one. Is this a basis for R2? Yes, it does. Again, we have to check these two conditions, right? Linear independence was the first condition and span was the second condition. So we have to check those conditions. So are these vectors linearly independent? The answer is yes, right? Because for linear independence, we just need to consider this determinant, and this determinant is really 1. The important thing is it's not 0. So they are linearly independent. And for bases, for span, I mean, span of these two vectors should be, so R2, which means I can write any xy as what? So I will write something here, 1, 0, right? And something here, 1, 1. So can we see what those some things are? So if you look at the second component, this is y, this is 0, this is 1. Which means this question mark must be y, right? So this must be y. Otherwise, it won't satisfy. So if this is y, then what is the first question mark? So what must this one be? So this is x equals something plus y. What is something? So what is this something? X minus y. Thank you. This should be x minus y times, let me make this better. So I choose this one. So x minus y times 1, 0 plus y times 1, 1 makes xy. So I can write any xy. I can represent any xy in terms of these two vectors. So this example shows that for R2, we can choose different bases. There is not just one basis for R2. We can choose different set of bases, okay? So this one is the most useful one, but sometimes for some applications, other basis vectors will be more important, okay, more useful, okay, depending on your application. So let's give a break here. Let me know if you have questions. Why is it x minus y? Okay, what? So maybe I should do it, okay? Maybe I should do it. So this one was like this. Okay, so there's A here and B here. So the question is, can I choose A and B so that this equation is true? Okay, so if you look at the second component, so the equations really look like this. X equals, is this the right one? No. So if you look at it, x equals A plus B and y equals 0 plus B. So the solution will be B equals y, and if B is y, then A is x minus B, which is x minus y. So we can always solve this system, okay? Ahmet, Emre. Okay, so this shows why B is y and A is x minus y. Okay, let's give a break here.